Hello. For this part 1 of the homework, we're going to be using closure, and we're going to explain a higher order function that accepts a function and returns a function that calculates the Jacobian of the central helical curve. And we're going to use a built-in function already in Python to prove that we were able to create a function that will be able to calculate the Jacobian. So we're going to be first trying to generate a helical pipe with the cross-sectional radius of 0.5 with the central helical curve defined by the following parameters, x, y, and z. And then we want to make this helical pipe go around in increments, and we want to make a coil around that pipe that we're going to be doing later in the later parts of the video. So what we want to do is we want to calculate the Jacobian. So the Jacobian is a matrix of multiple variables. So it's a derivative of function 1 over the independent variable 1. 2, also the derivative of all the functions to all the independent variables to all the functions to independent variable 1, and then from function 1 to independent variable 1 to the function of independent variable 1 and to all the independent variables. So you see how it is going here. So basically what the Jacobian does is it's just able to find the rate of change of a helix that is tangent to the plane. Okay, and we're also going to be using the gradient. We're also going to be using the gradient to find the Jacobian. It's very similar to the Jacobian, but the difference is it's in a single direction. So it's just a function. It's a derivative function to an independent variable to the derivative of a function to all the independent variables. Okay, so we're gonna first get into it. So a little background that I gave about the Jacobian and the gradient. So now we're first going to just generate this helical pipe. So we're going to go into Python and we're going to import numpy as np. We're going to import, we're going to do from plotly subplots import make subplots. So what this is going to do, the first one's going to import the numerical calculations, like just calculate like cosine, sine, and the second one's just going to make some plots for us. We're also going to import Jax. It's a built-in function to calculate Jacobian, but we're just going to use it to compare that function that we just made to calculate it. You'll see what I'm saying. We're going to run it. I don't know, it's taking forever. Okay, works. Nice. So now we're going to want to generate this helical pipe of cross-sectional radius of 0.5. So what we're going to do, okay, so we're going to make the radius radius 3, and we're also going to make mz, as you can see, is defined over here, 0.4. mz is just a slope, and then we're going to make it an increment of 50, and we can define t, which is the time it's going to be going around the coil. So we're going to start at 0. We're going to do 2 iterations up the graph. So np.pi and then increments with what it's incrementing through. We run it, everything looks good. Now we're going to define our functions time, just our equations. We didn't make a function yet. So y equals r times np. So this is just going to be in the x direction, the y is going to be in the y direction of the graph, and then z is going to just the slope and how much is incrementing up the graph. Everything runs good. So now we're just going to call that from plotly, we're going to be making a graph. So make subplots, figure that add underscore scatter 3D x equals x, y equals y, z equals z. And then we're going to we want to make it look pretty, so we're going to just say the mode is equal to lines. Wait, I'm trying to think about what went wrong. I see it over here. Oh, beautiful. Look how beautiful this looks. Oh, so you see we made a helical pipe that's going in 2 rotations, 4 pi. When you want to find a line that's tangent to this curve, to this line, so we can make a helical coil around it. So what we're going to need to do is we're going to need to take the derivative that is tangent to the plane. So the derivative, I pulled it up. So we're going to be taking this derivative at a point A, at a point minus a point that's infinitely smaller than A. So I think this has a better representation. So you see along here, you know how it's always tangent to the line? That's what we're going to be doing, is we're going to be taking the derivative of that. But first we're going to be using the gradient, because with the gradient we're going to be finding the derivative of the function over the independent variable 1, or the derivative of the function over all the independent variables. So we're going to iterate. We're going to use a for loop. We're going to iterate through the function, so we're able to get it in the x and y direction, in multiple directions. So let's just start it out so we can actually explain it. So we're going to define like cosine and sine, and we're going to store it in an array of values. So we can define a function of x, and then we're going to return np dot sine x of 0 minus, oh no, not minus, plus np dot cosine. So we're going to find it when sine is stored in 0, and we're going to store this array in 1. X of 1. We're going to run it. Looks good. So we're going to need to find a gradient for like single functions that is relative to each independent variable. So what we're going to do is we're going to define my grad. And what we want to do is we want to take the derivative in multiple direction, x, y, z, for the 3D curve. So we're going to define another function with that function, and we're going to call it get grad, like that calls for this, and we're going to store the independent variable x, and then we're also taking the derivative, so it's going to be 1 times e to the negative 10. We're going to make it a very small number. We're going to store that in we're going to store those values, and then we're going to define x plus h, and we're going to store these as a copy. And then we're gonna iterate through the entire for loop and range for I in range. X dot size X, and then we're also gonna go back to X plus H. So we're gonna be able to store these values. X okay, we're gonna store it in I plus H. And then we need to also define what the derivative is. So we do F under X plus H minus F of X divided by H. Okay, so now we're gonna do I think I messed up here. This does not look right. I actually meant to H of I equals X of I. That's what I was trying to iterate through this for loop. Because we're trying to define what X plus H is and we want to make it go through iterations. So we're going to do that again. Equals X of I. And then we're gonna append it, and we're gonna store the derivative. We're gonna append the derivative in here, and then we're gonna return the result, and then we're gonna return get grad. Let's run it. Everything looks good. Now we want to find a point where x is equal to -1, and we want to find where sine is equal to -1 and cosine is at 0. So what we're going to do is we're going to go through, we already defined the function, now we have to actually call it and use it. So we're going to do np.array, np.pi, np.pi, because we're going through a helical curve. F grad is equal to my grab the function f, and then f underscore grad of x of 0, call it, bam, we got our values of -1 and 0. So we're able to calculate the Jacobian using the gradient to get these values. Now we're going to prove it. Python has a built-in function that actually gets the Jacobian, so you don't even have to make this line of code. So we're just gonna, that's why we imported this earlier and how I was explaining it in the first part of the video. So we're gonna use that function. We're gonna define f underscore jax. It takes the independent variable x. We're gonna return jnp.sign x, first value of the array, plus jnp.cosine, and then we're gonna do 1, because it goes from 0 to 1. Jax. Now we're gonna call this function jax.grad underscore jax, and then we're going to do it through the first value of the, I was going so fast I didn't even think about what I was doing. JNP, okay, this is where the line, this is where stuff goes wrong. It looks like another parentheses, I think. Okay, there's one parentheses. I assume there should be an, x is 0. Let's try that out. Jax dot grad f underscore Jax. I don't know. I'm just thinking it might have to do with that. I don't know what though. So I'm just thinking what could have went wrong over here. It has to do with you know what? We could go to our old code and check it out. Or we could figure it out ourselves. Oh my god. Comparing the log code, return jnp.cosine. Oh my god. It was an X over here. So, as you see, we're able to get an array of values. And I don't know, I feel like that would belong there. But if I did it like this, yep, there it is. That's why I was wrong. See, it's all about the parentheses. So, very close to 1, -1, and this value is very close to 0. So we're able to confirm our results with the Jacobian. Alright, thank you for watching the video of me making this helical pipe and also this calculating the array that has the Jacobian -1 and 0. Thank you.